I think we lost your audio again, Felicia.
Bjorn just joined.
How's that? Are we back?
It's back.
Okay,
Yep.
sorry. Hopefully that's the last time. So there's the overview, and now I'm just going to get started. So this project, or this work was based on the Miracle project. It's focusing on, for INL, improving what distributed wind can do for resilience and cybersecurity in power systems. And for this portion of the project, we're focusing on resilience and resilience metrics. And specifically, how can we show that distributed wind, and more generally, we look at distributed energy resources, can improve resilience, and how do we quantify that, and then work to improve it. So there's a general need for resilience-based metrics, different than the typical reliability metrics that are used in power systems, that can show how the resilience of your system is improved. And so the metric that we have been working on, we call adaptive capacity. And that is, we define as how much power is capable of being transferred to critical loads before, during, and after events from all generators or specific generators. So this is DRs and distributed wind. And then that way you can also compare, there's certain generators provide more resilience value than other ones. And then you could go farther as basing that on location and other characteristics. So you can kind of think of this similar to contingency reserves, but it's a little bit different. And it takes into account the stability limits of the system. So what it is doing is increasing the amount of power that can be transferred to your critical load until you hit your stability limits. And this is all done with the ATC add-on in PowerWorld. So this is just a visualization of kind of what we're talking about. So there are two generators are providing power to your critical load, and we want to determine what's the maximum amount that we can transfer without hitting any stability limits. Typically, available transfer capability is used for interface transfers, thinking typically between balancing authorities. And so you're looking at how much power can you transfer across these lines that go in between these two areas or balancing authorities. And we're changing that to look at how much can we transfer to one specific load. So instead of across all these interface lines, how much can we get to a specific load? So it's a different approach, but using a method that's already established. And the tools that we use are the PowerWorld, which is a power system simulator, the add-ons SimAuto, and ATC. PowerWorld is a power system simulator. It's very similar to PSSE or PSLF, used for balanced transmission systems usually. And it has many capabilities. The most common that are used are power flow, contingency analysis, and transient contingency analysis. There's also many other capabilities I won't go into right now. I just wanted to show you a quick overview of what this tool looks like. So this is the main GUI homepage of PowerWorld. And what you're seeing here is on the right side is the system diagram of the 2000 bus synthetic grid system, which is overlaid on the geographical footprint of Texas, but it's synthetic. The folks at Texas A&M built this out. And on the left side is all the system data. So this includes your buses, your generators, and your load, and also any transient or dynamic models as well. And this is just an example of, so if you were to click on a generator or load in the system, either from the list form of all the information or from the diagram. What you'll get is the details of either your load or your generator, what you're looking for. So this includes your set points, and then also if you're including stability models, which would be your dynamic models, say for your machine, and also for your load. And these are also, there are also all these models for all components of the system, including lines and transformers. And so this is where you would find the most commonly used tools. So you see that's where you solve your power flow on the left, and this comes up when you hit the tool button. And then there's the contingency analysis. So if you wanted to do n-1, say line loss or equipment loss, that's where you would go to. So here's just a quick overview of kind of some example code from SimAuto. So what I showed you were where you would say open up your power system information and then perform a power flow or contingency analysis. And so you can do all the same, everything you could do from the interface, you can do it with SimAuto. And so this is some of the example code. All these codes and examples will be included in like a data packet for anyone interested so that they can test out the SimAuto and the tool that Hanwei built out. So the first portion of this code is just how you go through and open up the simulator and open up your case. And then in that middle section is where you would do any of your power flow analysis, contingency analysis, or transient simulations. And then you'd close up the simulator. And this is example code for if you were to want to run a power flow and then do steady state contingency analysis. This is just more here for reference, and all this code will also be provided after. So now I'm going to switch this over to Hanwei to go over ATC. All right.
Thank you, Felicia. Can you grant me the presenter's access, or I have to let you know if I want to switch to the next slide?
That's a good question. I'm not sure where I would do that. Let's see.
I can just let you know when I switch to the next slide, if that works.
Okay, presenter. All right, I think you ought to be able to now.
Yes, I have the presenter access now. Okay, hi everyone. My name is Hanyue Li. I'm a PhD candidate at Texas A&M University, and for this collaboration, I'm mainly, I guess, contributing my experience regarding the usage of PowerWorld and also using the SimAuto to automate the available transfer capability calculation. So the available transfer capability in PowerWorld would allow you to determine the maximum megawatt transfer between two parts in the power system, and that's known as the seller and the buyer in the power system, without violating any limits. And the typical inputs for the ATC calculation are a power flow case, a list of contingencies, and also the definition of the buyer and the seller in the specific simulation that you're interested in. The ATC will then determine how much power can be transferred between the buyer and seller without violating any system limits. That can be, transmission line limits or voltage limits, and we make sure that there are no system limits being violated, both in the base case and also the contingency cases. So I have a 5 system example to, I guess, to have a more, or have a less abstract way to illustrate the concept of ATC. So here in the 5-bus example, the seller is defined as the bus 2 in the system, and the buyer is defined as bus 3. And in the base case, for the seller right now, there's a, so for the seller bus 2, there's a generator attached to it with 280 megawatt of power injecting into bus 2, and for the buyer bus 3, in the base case, there's 118 megawatts of load attached to it. So to figure out how much power can be transferred between the seller and buyer, I would say there are generally two ways to determine the ATC. The first way is really manual. It's basically, we keep increasing the power injection from the seller and also keep increasing the power that's taken out by the buyer. And then for each incremental step, we solve for the power flow until there is one element in the system that reached its limit. So for example, when a system has no contingencies or no line contingencies, in this case, the limit, the transfer limit is 30 megawatt. If I increase the transaction between the seller and buyer by 30 megawatt, as you can see, let's say the load on bus 3 increased from 118 to 148, then I will have line 4 on the verge of getting overloaded with the loading being 100%. And similarly, if I want to take contingencies into consideration, I also have an example on the right. If the line 2 in the system is outaged, the available transfer capability in this case is less than the node contingency case, and it's only 15 megawatt. So if we want to, figure out the ATC for the whole system with the consideration of all of the contingencies, it will be the minimum or the smallest amount among all of the contingencies for all of the scenarios. And that, of course, is a very time-consuming process with lots of, contingency analysis and power flow runs. And most of the commercial softwares, including PowerWorld, uses or calculates ATC through the use of linear sensitivity factors. So when we are calculating the linear ATC values for the base case, we use power transfer distribution factors. It indicates the incremental changes in the real power that occurs on the transmission lines due to real power transfers between the seller and buyer. And similarly, if we want to calculate the ATC for the contingency cases, we use another sensitivity factor called outage distribution factors. This distribution factor is very similar to power transfer distribution factor, except that an OTDF provides a linearized approximation of the post-outage change in the flow on the transmission line in response to the transaction between the seller and buyer, whereas the PTDF only considers the base case. So that's a little, a math behind what the PowerWorld ATC is doing. And I actually prepared a short demo on the PowerWorld ATC user interface, but unfortunately, my Office desktop updated overnight, and I just lost my PowerWorld license. But luckily, I have all of the screenshots for the software, and I have all of those screenshots for the user interfaces. So let's say, for example, for the project that I'm, that we're working on, we want to investigate the available transfer capabilities with the definition of the buyer being the critical load in the system, and the seller can be, all of the generators in a certain area. So in this example, my seller is defined, or my buyer is defined as a load 1064, and that's the bus number. And the seller in this case, is defined as all of the generators in the same area as bus 1064, except for the generators attached to bus 1064. So the first step that we need to do is to define the buyer and seller injection groups, because we are considering a cluster of generators as an injection group to be the seller. So in PowerWorld, if you go to the case information and I think it's called Model Explore, and under the aggregation tab, there's a subtab called injection groups, and that's where you define your injection group. And after we have the injection group defined, we can go to the ATC add-ons. So the add-ons is under the add-on tab, and if you click on the ATC tab, you will see the user interface for PowerWorld available transfer capability calculation, where in the red boxes you can define the seller and the buyer, and also play around with the key ATC settings. And in this example, we are defining the buyer as the bus 1064, and we're defining the seller as injection groups that we just created. And here, I guess the key ATC settings are we are using the lossless DC linear calculation method, and we included all of the N-1 contingencies in the system. Oh, also, by the way, this test case is a 2000 bus synthetic system on the footprint of Texas. And so the contingencies should be around the order of hundreds. So there should be like hundreds of contingencies included in the simulation. After we defined or finished the ATC simulation settings, we will go to the analysis tab and start the analysis. And then we can also go to the results tab to see the results. And I will explain what the results means in a bit detail later. But because I don't have the demo, to show you guys live, but it's actually a pretty fast process because it's a linearized approximation. So it only requires the power flow analysis for the base case, and for the contingencies, it's a linearized approximation. So it's a fairly fast process compared to the 5-bus example where you have to play around with power flow and eventually see if you have any elements being overloaded. So that's a general overview of the PowerWorld ATC with an example. And for the adaptive capacity tool that we developed, the purpose of the tool is to automate the ATC calculation in PowerWorld in a large batch with user-defined buyers and sellers. Because if we are using, the PowerWorld user interface, it's great. It's very straightforward, but there's a lot of button clicking. And what if I want to, simulate 1,000 different buyers and 1,000 different sellers, and it will take a lot of time if we want to just finish, if we just want to complete the task within the PowerWorld ATC user interface. That's the purpose of us developing this tool. And so for this tool, the only user input that that requires the future users to change is, first, for sure, you need to specify the directory and the name of the PowerWorld PWD file, which is the PowerWorld PowerFlow file. And the second step is to specify the type of seller and buyer. So to be consistent with the demo that I just did, or the PowerFlow or the PowerWorld user interface example that I just did. So in that case, the buyer type is specified as a single load bus because it's the load bus number 1064. But this code can also take the buyer type as multiple load buses as a cluster, as like multiple load buses as one single buyer. And for the seller, to be consistent with the example before, here we chose the seller to be area generation, which means it's all of the generators in the same area as the buyer. but we can also take stellar type area Jan wind, which is all of the wind generators in the same area as Bayer, and also area Jan DER, which is all of the distributed energy resources in the same area as the Bayer. And we can also, instead of the area levels, we can also specify the stellar type to be on the zone level as well. And the third step is to specify the stellar and Bayer bus numbers if applicable. And in this case, we specify the Bayer number to be 1064. And for the stellar, we don't have to define it because the code is going to automatically create filters to filter out all of the generators in the same area as Bayer. And the last step, of course, is to specify the output file path. So the ATC calculation results are going to be saved as a CSV file in the specified output file path. And this slide is talking about the ATC simulation details that we have in the tool developed. As I mentioned before, there are two types of Bayers that we accept in this tool, and also there are 6 different types of stellars we accept in this tool. And for the ATC simulation details, it's consistent with the ATC user interface example that I just did, where we use the lossless DC as the linear calculation method. And also, I think it's important to note that when we define an injection group with multiple generators, we use the generator maximum capacity as I guess the reference to the participation factor, where the participation factor of generators are proportional to its maximum capacity. And this slide is talking about the output results, and the picture on the right is basically the output file that will be spit out from the tool that we developed. And if you compare the result in the spreadsheet with the picture several slides ago for the PowerWorld ATC user interface example, all of the numbers are consistent. And so for each, of course, in the spreadsheet, we will tell you what the stellars and the Bayers are by the user's definition. And then for each row in the spreadsheet is different. It's different contingency rounds that if we apply this contingency, then certain element in the system has violated its limit. For example, if we look at, let's say the first, or in the spreadsheet, it will be row number 4. So the limiting CTG is basically the limiting contingency. It's the contingency once it happens, it causes trouble in the system, or it causes violations in the system. And this violation, the limiting element is specified in column B. And for this limiting element, we use the limit in column E. And after the contingency occurs, we use the linear approximation to approximate how much flow will be on this limiting element. And you can see here is 285 megawatt, which is more than 225, which is the limit for this element. And that's why we mark this contingency out, because it's basically causing trouble in the system. And I guess the last field that I want to talk about is the transfer limit. So this is the amount of transfer that can occur in the base case before the limiting element before the limiting element reaches its limit after the contingency occurs. And that's everything I have. And I will be giving presenter right to Jess to talk about the visualization.
Hi, everyone. My screen is still loading, so I'll hold off on the, oh, there we go. Anyway, my name is Jessica Wirt, or Jess. I'm a grad student at Texas A&M, and I'm working on the visualization component of this. So the visualization that I'm going to be presenting in an example is called the Pseudo-Geographic Mosaic displays. So this concept is presented in the paper referenced at the bottom of the screen if you have more questions or are looking for a little bit more in-depth of an explanation into this. But essentially, this is one visualization approach that is tackling the trade-off between communication of information and using display space effectively, so that hopefully you can communicate the information within one quick snapshot. So the example that I have right down here is the line loading. And so this case has over 3,000 lines. And so each of these little tiles that you see is representative of one line in the system. And so the metric that we've chosen to visualize in this screen is the line congestion. And so per the color gradient on the left-hand side of the screen, you can see that the darker blues are the lightest loaded lines and the greens are getting into like more heavily loaded lines, but they're still relatively lightly loaded lines as this is a low load case. So what the pseudo-geographic mosaic display does is it represents each of these system elements as a tile. And you can select if you kind of the degree of transition from the whole picture of the mosaic to you know, really preserving the geographic relationships of the 0% transitions, but you don't get quite as quick of an information transfer with that. So this is just so in one glance, you can kind of have a picture of what the system is. So if you're considering a mosaic tile that is in the upper right-hand corner of the mosaic, then that is a more northeastern line in the system that's being represented. Oh, I'm not sure I have control. Oh, there we go. So a brief introduction with, oh, how can I go back here?
Sorry, I still end up having control. I couldn't get it to switch. So if you want to go back and forth, just let me know.
Yeah, if you could go back one previous slide. Oh, great. Sorry, I thought I had the transition slide in there. We're going to go forward one slide. Thanks, Felicia. So how to do this in PowerWorld. This is something that is possible to implement outside of PowerWorld, but it's really easy to do inside PowerWorld if you have version 21 or beyond. I believe 21 is the latest version that's released. So if you have 21, this is feasible. But how you do this is you navigate to the Model Explorer in Case Information. And then on the left-hand side of your screen, you can choose which system element that you're considering to visualize here. And then once you've selected the element for visualization, you then go over to the exact metric within this element that you would like to visualize. You give that a right click, and then you have this drop-down menu. You select Geographic Data View, and then you have it select the whole column, then bring it to Geographic Data View. Next slide. Felicia?
All right, let's see. I have the...
Great, thank you.
Mm-hmm.
And so once you select that Geographic Data View button within the dropdown, you are presented with this pop-up that is on the left-hand side of our screen right now. And all you need to do is press the button at the very bottom, add Geographic Data View objects to the one line and close the dialog. So what this does is it establishes an element within the one line. It's by default a rectangle that you can change how it's represented in the case. So it adds it to the one line, and then you're able to navigate to the one line. And if you right-click somewhere on the page of the one line display, then you're able to navigate to the GDV form, which is where you can go ahead and edit these geographic data view elements. And so once you're in here, elements that I find really helpful to tweak when adjusting a visualization would be line thickness. You could have the line thickness correspond to different components of the element that's being monitored. You can also customize exactly how you would like the color map to be. So if you would like it to be a discrete mapping, if you'd like it to be continuous, if you'd like it to be on a grayscale, or there's a whole assortment in there, and you can also add your own new color maps in there as well. So that's a really great place to do it. Something to note is it's helpful if you're comparing multiple different pseudo-geographic mosaic displays to make sure that these color scales are on the same level. So if you're working with a percentage, it does make sense to do 0 with a nominal of 50 and maximum of 100. But there are other cases where those values don't make a lot of sense, or if you want to get a little bit more variation in the colors of a system, you might want to narrow in on a region, but it's important to note that you'll have to be careful to make sure that those are the same, so you're comparing apples to apples in your quick snapshot visual. And then also, if we go to the right, you're able to specify the transition details. And so this is done by navigating by the top tabs on this pop-up display, and you can select kind of that percentage of transition. So if you want it 0% transitions, essentially they're just little tiny tiles that preserve complete geographic, their true geographic location, or 100% where it's the pseudo-geographic representation, but you're able to communicate a little bit more with the colors. Then you can choose to select that and apply it or restore it from the mosaic view within that tab. Next slide. Excellent. Thanks, Alicia. And so for these cases that we have here, this is one adaptation of the Texas 2000 synthetic case. And so the representation that I have in the bottom is from the low load fall case. These cases were introduced, it's a set of 8 cases that are prototypical for high or low load scenarios of the case for each season of the year. So we have high and low load for spring, summer, fall, and winter. So this is for the low load fall case. And the buyer is a single load buyer, which is bus 4040, located down in Callan, Texas. So it's circled down there at the southern point of Texas. And the seller for this simulation was selected to be all area generators. So what that means is that the responsive generators here are going to be located south of that black dotted line, or in a pseudo-geographic mosaic display, or PGMD representation. You can look to the figure on the left of the screen, and you'll see that that area, the buses are mapped to the lower component of the screen in the green displayed there. So a quick snapshot information about this case: 2,000 buses, 544 generators, about 3,200 branches, 8 areas, and 28 zones. So there are a lot of different ways to consider the information from this case, with just considering it, dividing it by those different elements there. But the following example is going to be for the looking at the branch loading in the case. Next slide. Excellent. And so this is, and Felicia, could you press it once more? Excellent. So if you'll remember from the previous slide, this is the area about where the mosaic tiles from this region are mapped. And so we do notice a few changes within this region, most notably on about the 6th column over, when we add the capacity to that buyer load, we do notice additional congestion in this region of the system. So in this one snapshot, we have a little bit of an idea of where in the system this congestion is taking place. And with a quick sanity check, it does make sense that it's in the same region of the system that the buying and selling has taken place. So as an explanation of this visual, on the left-hand side, we have the mosaic display from the base case. So absolutely no change is being made, and this is for for the load base case. And then on the right-hand side, we have just added in that additional load, so that additional capacity that was identified from Hanyuli's code. We've added this higher load. Each of the mosaic tiles in this case represents a system branch, and their color is mapped to the line loading. And next slide. Thank you. So there are a lot of different potential opportunities. There are a lot of different angles that you can communicate this information from, and it's really exciting to be beginning to approach this. So as you see here is a visualization metric that we chose line loading, but you could also look at it from
Hey, Jess. Okay, can I interrupt you for one quick second? There's a lot of background noise. I'm curious if it might be coming from your mic. I just wanted to check.
Sure. Is this better?
Say again?
Is this better?
Yes.
Excellent. So the visualization metric, what we have here is the line loading, but you can also look at it from the voltage perspective. You can look at it from the transfer capacity, looking at that metric that came from the ATC code. You can look at it from the perspective of defining the buyer and seller differently, or with different load conditions, or throughout time. You could look at it from considering limiting contingencies, or in different styles, such as the PGMD, as I walked through the example of here, using contours, which is very common when presenting bus voltage, or it's really neat to imagine static or dynamic or even interactive ways of communicating this information, where perhaps the user might be able to scroll through a timeline of what a year might look like, or select different buyers and watch the visuals change in front of them. So these are ideas that are kind of on the back burner right now, but there's definitely a lot of potential here for how to communicate this information as well.
Great, thank you, Jess. So now I'm just going to wrap up with what we have plans for next steps. We'll be submitting a conference paper that goes over the adaptive capacity metric and how it's calculated using examples from the 2000 bus synthetic grid system, comparing seasonal and loading scenarios, and comparing different types of generators and how there's a difference between the adaptive capacity based on those generators. Now we'll also be working on building out more of the visuals. Now, after this webinar, I'll be sharing a folder, probably on Box, that will have an example of all of the PowerWorld test cases and the code for the tool, example results from the tool, and also just a short example code written out in SimAuto for doing general PowerWorld, normal power flow and such. So now I have questions for the general audience about this work, which are, would this tool provide use to the systems that you work with? And then also, what tools and test systems do you use? So this is all built out in PowerWorld, but I'm curious to hear if any of you think that this would be useful if it could be built out in another tool. I know the PNNL folks use GridLabD a lot. So I'd be interested in your perspective there and any other input. And also feel free to interject any of your own questions about this work now. So I will open up the floor. There must be questions. You can also put a question in the chat conversation box if you'd like.
So one of the questions I have, and you may have covered it, at least your expectation, but I'll ask it anyway. What's the long-term strategy, if there is one? I know that you're all students or completing students, Felicia's case, what's the long-term strategy of what you're looking to do with these approaches? I mean, is it kind of a one and done sort of thing, or is Texas A&M going to continue to use it? I mean, we've been doing the adaptive capacity thing for a while, as Felicia knows, and we have other areas that we're applying it to that Felicia may not even be aware of as we continue to evolve it. But I'm kind of curious what the long-term strategy is, or if there really is one.
I'll say from the INL side, from my perspective, is it'd be great to continue using this, and the benefit of having this all in a tool, code-based tool, and there's only a select user inputs, that this can now be more easily used by anyone. You don't necessarily have to understand all of the components of PowerWorld to be able to run this. So I imagine that INL will continue to use this, and because it's kind of built using all the PowerWorld tools, I'll let Hanwei and Jess see what they think about this, but if this is a well-received metric, then it's not completely out of the question that this couldn't get wrapped into kind of part of PowerWorld in the future if it's well received and we keep the collaboration going. I don't know if Hanwei and Jess have anything to add to that, or Jake from the INL side.
Yeah, I mean, I'll jump in. I don't want to have too specifics of where this is headed, Craig, but obviously, you know, we've got a handful of projects that are leveraging this capability. You know, some of the opportunities to partner with other models and other efforts is obviously strongly advised. We've got some unique projects funded through GMLC that I would like to start, you know, coupling up. So Miracle is one of those projects that, you know, Felicia obviously has laid a foundation of great work to be started under. But another project like Flex Power and a couple others that the Plum Island Black Start project as well. Those are all distribution-based projects that have, you know, a lot of hardware-based controls and different market pricings, and you know, there's just a lot of opportunity for all of this work to be expanded into multiple research areas. When we think about some of our DoD applications, this is a capability that could be packaged up. I mean, right now it's a little I don't know how to phrase it properly, but it's a little disconnected, if you will, from maybe some applied microgrid projects. But I can definitely see how it could be expanded to be unified into a kind of a tool suite. I don't know. I think the opportunities are endless. It's just, you know, where are, you know, I know where Felicia's headed. I know how to get a hold of her. But Hanwei and Jessica, you know, that's an opportunity to further the conversation. Is where are your interests headed? Do you have, you know, classmates and other professors or mentors looking at using this work for some of their follow-on research? Yeah, a lot of questions, Craig. I don't know that we have direct answers yet, but
So it'd be interesting, I think, to have a dialogue on that particular concept, because right now resilience metrics are in vogue, as all of you probably know, and nobody's accepted anything in particular yet, and probably won't for some time. There's a number of variables. I'm being very myopic and probably just mentioning a few. It's got to be easy to use if you want the power community to use it. Power engineers might themselves, if they're doing design, might get into something a little bit different application there, but it's got to be simple enough to use. And where you have an opportunity to actually embed it in a tool that they may use. Not sure how widely used PowerWorld specifically is for power engineers, but there's a way to do that. I think that'd be really interesting, and it'd show immediate impact, because if you got something in a tool that they recognize, and they can start utilizing it. We've got some other tools that are kind of on their own in a way, and that provides maybe a different benefit. Some of that's going to go from planning to operation. So redistributing the power after a cyber or physical attack. Have you, any of the folks that from NM or Felicia, have you reached out to the developers of PowerWorld to see if this is something they're directly interested in?
I have a contact at PowerWorld, and I know Justin and Hanue do too, because they're both students of Untitled Overview. But we haven't reached out to them directly yet. We wanted to send out a paper first and get feedback.
Yeah, and that's probably the appropriate thing to do. But it sounds like you have a contact, and that's really what the direct initial question was of mine, so you could start socializing it. One of the things that you may want to consider, and maybe it's a late in the game, and maybe it would be a follow-on, here again following your plan, would be to include them on a paper and just say, hey, we're using it for this. We'd like to have you on a paper. And I think that could step you in the right direction, but you may have already thought of that. That's just something that occurred to me.
Great, thank you.
Hi, Felicia. This is Julia from PNNL. Question about these synthetic grid models. This one for Texas, it's great. How long would it take? Are there models available for other utility service territories or reliability areas? How long does it take to develop something like that? And are there others available?
Hanwei, do you want to jump in there since you built those? Well, oh, there she is. Okay. Well, how do we build out the system, the 2000 bus Texas system? If she drops back on, I'll let her talk for herself. And so these are all built with machine learning, and there's several other test cases available. I think they're on the Texas A&M website. And so there's some as large as the entire Western Interconnect. And they also have an Eastern Interconnect one, I believe, and some smaller ones for like regional areas of Illinois and South Carolina. I'm not sure about how long it takes. Oh, there she is. Yeah.
Hello, I just got disconnected. But yeah, to answer the question, so the synthetic test cases, the test case on the footprint of Texas has 2,000 bus, and we also have a larger system on the footprint of Western Interconnection with 10,000 buses, and also a 70,000 bus system on the footprint of Eastern Interconnection as well. And for the New England region, we also have a 25,000 bus system. And also, of course, there are some smaller ones, as Felicia mentioned. There's, I think it's a 200 bus system on the footprint of Central Illinois.
And I'm sharing the link in the chat now for access to those.
Thank you.
And I think regarding the applications of this tool towards larger test cases, I think the tool is developed to be really flexible. It's just we need to, if you want to use it on the larger cases, you just need to have the PWD file for the larger synthetic test case.
I have a question about the tile visualization component. So how do you guys decide which buses go in a single column? That tile, is it just geographic approximations, or is it something else?
It's approximately geographic but the exact layout algorithm that's used in PowerWorld, I believe, is based on the tree map layout algorithm.
Okay. So you kind of just take that algorithm and use it to define which buses get stacked in per column.
That's correct. And it is possible in PowerWorld as well to specify the column width as well. So you can kind of play around with that.
Cool, thank you.
You're welcome.
Are there any advisory board, Miracle Advisory Board members on this call?
There was. I noticed we had Rob Wills on for a little while, but it doesn't look like anybody's remained unless someone's on the phone.
Okay.
Yep.
All right, well, we are available if anyone has questions in the future, and I'll be giving everyone access to all the files and information and also this presentation, and you can feel free to reach out to us. This is all our contact information. Thank you so much for joining the call today, and have a great rest of your week. Thank you.
Thanks, Lucia.
Bye. Thanks, everybody.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.